We would start in 4 minutes, but let's start right now because I've got like loads of content and I'll probably run out of time anyway. I want to play a game. Actually, this talk is about machine learning and game theory. And let's start with a very simple game. It's a tree structure. The computer, we start. And our goal is to get the highest score, which is basically in all games, right? There is also an opponent, and he wants to make sure you don't have the highest score. Depth 1. This is pretty trivial. We go to the left, we get 5. We go to the right, we get 3. So we go left, 5, we win. When the game tree gets a bit larger, problems start to arise. Should we go left or right? Immediately, it isn't trivial anymore because we do a turn, then the opponent gets a turn, then we do a turn. So what would be the best path? Well, actually, there's a well-known algorithm to do this. This is called minimax. So when it's the opponent's turn, we minimize the maximum score. When it's our turn, we maximize the minimum score. And basically, we know the end result. We know there's all these numbers in the end nodes. So it's perfect play. Both players know this, so we can just calculate. The thing is, you start at the bottom. It's our turn. So with 3 and 5, we pick 5. With 9 and 2, we pick 9. 6 and 8, we pick 8. We pick the highest, obviously. And then we calculate all the way to the top. It's the opponent's turn. So instead, 5 and 9, he'll pick 5. He wants us to get a low score. And 8 and 4, he picks 4. So we have to pick 5. And, well, we both play perfectly. We are computers. So we'll end up at 5. That's the best case for both players. Any other case will turn out worse for you. In this simple game, we have a branching factor of 2. At every node, we split in 2. It's called the branching factor. And we had a game depth of 3. And it had perfect information. Everybody knew what every node, the value had. Everything's known. So we can just calculate everything, and it's known. So let's take a more advanced game. Let's look at noughts and crosses. Any Dutch speakers, in Dutch it's butter, cheese, and eggs, which doesn't make any sense at all, because the game of noughts and crosses has noughts and crosses. The game of butter, cheese, and eggs does not have butter, nor cheese, nor eggs. So, yeah, let's keep it at noughts and crosses. This will be the game tree for noughts and crosses. We'll start with an empty board, and you get 9 choices. The first one is you put an X here, you put an X there, you put an X there, etc. So, if you have enough paper, you can draw this entire tree. And at the bottom, you can assign a value to the nodes. So, for example, 1 if you win, 0 if there's a tie, and a -1 if you lose. If you would make this entire tree, at first step, there are 9 choices, and then there are 8 left, and then there are 7 left, there are 6 left, there are 5 left. So on average, each node branches out 5 times. That's more than the game we had before, which had 2, so now we have 5. The maximum depth is 9, because after 9 moves, the board is filled. You can't do any moves. It always ends in 9 moves. And if you paid attention in this game, there's a lot of rotational symmetry and mirror symmetry. And if you remove all these symmetries, there are just 138 terminal positions. So in 91 times, the one that starts wins. In 44 times, the one that goes second wins. And there are 3 possible draws. If you do the minimax algorithm on this tree, for a computer, this is still a very small tree. You always end up in a draw. This game is solved. We have perfect information. It's always a draw if you play perfectly. More advanced game, chess. So this is a chessboard, and well, if you start with an empty chessboard, you've got 20 moves to make. So this game is the game tree of this game is even larger. You can see it even more clear in this example. At depth 0, we have just 1 node. That's our start board with all the pieces in the start position. At the first move, there are 20 possible moves. So white has 20 moves. Then it's black's turn. Black has exactly the same pieces, so he has 20 moves too. That makes 400. And at 3, things get interesting. There are already 8,902 different nodes. And there are 34 captures and 12 possible checks. And as you can see, after 4 moves in chess, it's even possible 8 of those moves end in a checkmate. So you can win chess in 4 moves if the opponent makes stupid mistakes. But as you can see, after 6 moves, you're already at 120,000 million, 120 million nodes. And this keeps on growing. So with every move, the branch factor is so big, it keeps on growing. This is actually known as a perf table. It stands for performance test, and I've made my own chess engine, and it's perfect to validate your chess engine. So the only thing you need to do is generate all possible moves, and from those moves, generate all possible moves, and from those moves, generate all possible moves, and you just count what happens. And if you're lucky, after 6 iterations, this number rolls out. And when you're building a chess engine, you have like 119.060.322. Oh, god damn it. I'm missing 2 valid moves. So, and there are even more examples where you have like a setup where you have a lot of castling and promotion going on. And people have created perf tables for this with chess engines. And you can use it as an integration test and make sure your chess engine still works. Chess becomes too large. You can't write it on disk or keep it in memory. This entire tree, it would take years to compute, decades to compute. So both players don't have all the information. So how do we say a node is good or bad? We have to use an evaluation function. And it turns out in chess, it's very easy. The most simple evaluation is just count the pieces. If you've got more pieces than the opponent, you're probably ahead. If you don't have a queen, you're probably behind. So it's pretty easy to have an evaluation function for chess. On average, for each chess position, there are 35 valid moves. This is just an average. So we start out with 20 valid moves, and then you open up the board, and there are more moves possible. And also, on average, a chess game lasts for about 50 moves. So in total, if you want to calculate on average how big the tree is, it's 35 times 35 times 35 times 35. This 50 times. That's an incredibly large number. This is too large for computers to compute. But the evaluation function is easy. So what you can do is just do like the perf table we did before and stop at the depth of 6 and evaluate all the nodes and see which are good moves and which are bad moves. And what you can also do is pruning, which means you can cut entire branches out. So for example, if you lose your queen, stop evaluating. This is probably not going to end well for you. Also, if it's like the opponent sacrifices his or her queen, that's probably not going to happen. You can dream about it, but don't waste CPU cycles on it. Advanced chess AIs can look 20 plus moves ahead, and well, yeah, it's been beat. You can't beat the computer. Even my computer here, it can beat the best professional chess players. On to the game of Go. You've got a 19 by 19 board. It's got black and white stones. You take turns. One is black, the other is white. You can place them anywhere on the 1919 board. And the goal is to surround areas and capture the opponent. So what about this complexity? There are a couple of problems here. The branching factor in Go is 250 on average. That's much more than chess. Chess had 35. So at each node in Go, you get 250 times 250 times 250. This is the second problem. You don't stop after 50 moves, because Go usually lasts for 300 or more moves. So the search space is enormous. And then there's another big problem. It's almost impossible to write a good evaluation function, because in Go, your goal is to capture an area. Maybe you are 90% there. You just need 2 more stones to complete it. But other stones could prohibit you from completing that circle. So even though it looks like you might have an area, you might never be able to capture it. And this is almost impossible to calculate. So where chess has a very easy evaluation function, in Go it's like if you ask a good Go player who's winning, sometimes most of the time they agree, but then you say, okay, how did you calculate it? It's a hunch, it's a feeling. It's all about feelings, and we can't program that. So if you would take a Go board and you ask, okay, how many different positions can you put a Go board in? This is the number, and that number is larger than the amount of atoms, someone's calculated it, I didn't count, in the entire universe. So what they do instead is they do a Monte Carlo tree search. Monte Carlo is known for the nice harbor and the view, but also for the casino. And in a Monte Carlo tree search, you pick a node, you play randomly or semi-randomly to the end, and you see who's won. So you either get a 1, a 0, or a -1. And you do this as often as possible, and this gives a very good indication. Especially near the end, there are less nodes below you, and you can calculate more because there are less nodes to calculate. This gives a good indication if a move is a good move or a bad move. And this is how almost all the Go programs work. They just use semi-random moves to decide if it's a good move or a bad move. Last year, the experts said it will probably take 10 to 15 years before a computer could beat a professional Go player. And suddenly AlphaGo was there. AlphaGo is created by Google DeepMind. First it was DeepMind that was acquired by Google. And it works using neural networks. A neural network is a computer model based on biological neural networks. So basically it's a computer model of your brain. This is very simply how it works. There are some input nodes, then there are hidden nodes and output nodes. You give it a binary input, this is either on or off. These are connected to all the other nodes, and these are connected to all the other nodes, and usually there are much more layers than this. The layers have certain strengths and thresholds, and some of the nodes fire, and then some nodes fire, and eventually some output nodes fire. And using this, you can train the network, and it gets smarter, and it recognizes stuff. So what did they do? They first started with something they called a supervised learning policy network. They took 30 million amateur matches, and they set the goal to predict the next move. So the neural network was trained to predict the next move. And it got a result of 57%. So in 57% of the time, it predicted the same move as an amateur player would make. So yeah, it's a result. It's not very good, but it's a result. Then they created another neural network. This is actually a copy of the first network. And the new goal was to predict the best move. So not the move the amateur would make, which might not be the best move, but the best move. So how did they do this? Well, they just had a lot of copies of the same neural network, and it would play itself like 1.2 million times, took 1 day, and it would keep playing itself and tweaking itself. And that way, it would play until the end, and it would see which network was better, and it would pick that network. Then they pitted it against Pachi. Pachi is like a reasonably strong AI, not the best AI. And it won 85% of the time. And that's without searching. That's just at each node, what is the best move? This is the best move. So that's pretty powerful. But they did want searching. They didn't want to just have the neural network. So what they did, the network we were talking about earlier, is pretty slow. It takes 3 milliseconds to evaluate one node. Doesn't sound very long, but if you want to do a Monte Carlo search, for example, you want to go to the end as fast as possible. That's why they created this network. It's a bit simpler, but it's based on the previous network. They just tried to make it as fast as possible by seeing if they could remove stuff and keep it almost as good, but much faster. And they took it down to 2 microseconds, which is 1,500 times faster. So that's a good result. And this one is used for the Monte Carlo search. Yeah. Yeah, the question is, how did they make this faster? I'm not sure how they did that, but my understanding is they had a very tiny neural network, which was much faster, and they trained it to be similar. So they probably did self-play there. They created a fourth neural network. This is the value network, and this is actually to do the evaluation function. So they trained it using the same 30 million games, but its goal was, okay, given a board, tell me the winner. Who's winning? Initially, it had 0.37 error, which is pretty big. 0.5 would be random moves. But after self-play and self-training, it came down to about 0.23, which is okay. So in more than half of the cases, it would correctly predict the winner. So they went on testing this network. So for a given board, it would generate all possible moves. And for all those moves, they will pick the most likely, the situation where we are most likely to win. So this is not really searching, but just one-step searching. This network beat the strongest Go AI that was written without actually doing a tree search. So they went on combining all the pieces. They used the policy network to look for the best moves. Then they checked with the value network. Are we winning? And then for the moves that were still left, they did, with the very fast rollout network, they created Monte Carlo tree search to the end to give it an even better, evaluation. And then they talked to Lee Sedol. He's regarded as the best Go player of this decade. I think he's currently 5th in the world or something, but he's been dominating the sport. He's compared to Roger Federer of tennis. He's the Roger Federer of Go. So, best of 5, the winner gets $1 million. Just so Lee Sedol really tries. This is Lee Sedol after losing 4-1. He wasn't happy. So, yeah, it's fun. We cracked the game. We've beaten a professional. So Google DeepMind did a very good job. But why is this important? You have to remember, nobody told AlphaGo what a good or bad move was. Nobody programmed an evaluation function. It doesn't know the game of Go. AlphaGo isn't an expert system. AlphaGo learned by watching others and self-play. And it used general machine learning techniques to figure out for itself how to win at Go. And that's special. For the last 20 years in AI research, almost nothing happened. And suddenly, with the new neural networks, and you see it in TensorFlow and now with DeepMind, I think this is really the start of the AI age we're entering. So watch out, Skynet. That's it. Our time is up.